Good morning, everyone. Today we start our ninth lecture, and as we agreed last time that we start every lecture with like going through the last quiz. So this is quiz number 6. This was the last quiz, and last quiz is there's 3 problems. There are 3 problems, as you can see. So the first problem is random variable x has a uniform distribution from -4 to 4. Find this characteristic function and use the derived characteristic function to find the expected value of x3. Okay, so of course, we have already derived the characteristic function for general uniform distribution. Let me go to the slide, to the lecture, to the chapter. I think it would be. Yes, it is already here. Yeah. So should be somewhere. This is the part of the stochastic process, but before that, we have the characteristic function topic, where we have we find the expectation of e of the power minus or of j xt or yt. Should be yes. Yep. So derive the characteristic function of the uniform distribution x from a to b, and this is the result. So that sorry, this is the result. Yeah. So the result is equal to e to the power jpt minus e j at divided by jt and b minus a. So in the quiz we gave that what is a and b. So it was from -4 up to 4, from -4 up to 4. So if we keep this and let us open the whiteboard to write. Yes. So maybe now you can see the whiteboard. So the equation was, as we saw it, so it could be written that the characteristic function equal to e to the power j bt minus e j at divided by jt times b minus a. Okay, so in that case, so yeah. So in that case, we have b equal to 4 and a equal to -4. Okay, so this equation becomes e to the power 4t minus e minus j 4t. 4 minus 4 is equal to 8, so it will be j8t. We know that this ej4t equal to cosine 4t plus j sine 4t. And this one will be cosine 4t minus j sine 4t. So, and we have minus here. So cosine will cancel cosine, and then we have 2j sine 4t divided by j8t. Okay, so j cancel j, and 2 it will be 4. So finally we will have sine 4t divided by 4t. This will be the characteristic function of this uniform from -4 up to 4. As we saw before, that if you want to find the expected value of x, then this will be the differentiation of this phi x of t with respect to t, and here divided by j, and we evaluate it at t equal to 0. And the same thing can be done for e of x squared. It will be the second derivative for this one. So it will be d squared phi x of t divided by dt squared, and this will be minus because it will be j squared is minus. And then the expected value of x cubed will be the third differentiation of phi of t with respect to t, and it will be divided by j. So this is the expectation. If you want to expectation for, it will be the fourth differentiation and so on. So what you need actually is to differentiate this one 3 times and then evaluating the differentiation at t equal to 0. The differentiation 3 times of this one is straightforward, but it takes time. It takes time if you differentiate this one, because, for example, if I want to differentiate it one time, so it is sine 4t divided by 4t. If you differentiate it one time, so d phi over dt, it will be, you can take this 4t square and then cosine 4t multiplied by 4, okay, times 4t, or we can keep this, okay, it is not a problem, so we can 4t, and then it becomes minus, the differentiation of 4t is 4 times 4t. So this is the one differentiation. So you can cancel 4 with 4 and so on. But then if you want to take the second differentiation, it will be even longer in this case. And this is the reason that when I last time the lecture, I give you that you can use Octave. You can use Octave for symbolic calculation. Let us do it together, so you know how to use these resources that you have. Okay, I will share. So I will now we try together to evaluate the third differentiation of the equation with Octave. So of course you can do it with hand. It is not complicated. It is only lengthy. It takes maybe 1 or 2 pages of derivations, but it is not hard. You can do it easily, but still I show you now how could use it with or solve it with MATLAB or Octave. Okay, so now I need to load the package of symbolic. In MATLAB you don't need, because it is already built in, but here I need to write package load in Octave, package load symbolic. Okay, so now the package has been loaded. Okay, actually it comes when you install Octave. This is version 8.4 or 8.3. It comes built in already, but you need to load it. Then I need to define t as a symbol. So t equal to symbol of t. There are different ways to do it. Takes some time. Okay, now it has defined t as a symbol. So now I need to define my function. So my function is that x equal to sine 4 times t divided by 4t. 4 times t. This is the function that I have right now. So this is the function x equal to sine 4t divided by 4t. One thing that I want to show you now, you know that for the characteristic function at t equal to 0 must be 1. The characteristic function at t equal to 0 must be 1. So now if you substitute with t equal to 0, it will be sine 0 is 0 divided by 0. 0 divided by 0 is undefined. Okay, is undefined. But actually, if you take the limit, when t goes to 0, this will be 1. And let us try. So if we put t equal to 0, then we say substitute in the equation in x, none a number. It gives you none a number. Why it is none a number? Because 0 divided by 0 is not defined. But if you take the limit, okay, of x, I think it is written in this way. Maybe it is limit. Yes, you can see that when you take the limit, it gives you the result is 1. And just to remind you about some basics, that when you take the limit, when it is 0 divided by 0 or infinity divided by infinity, it is called Hopital rule. Hopital rule, we took it already in math 2, in bachelor, and our bachelor, I still remember it. So Hopital rule that you differentiate both. You differentiate sine and you differentiate this 40 and then substitute at your limit that you want to reach, and then you will get 1. So this is important. The characteristic function at t equal to 0 must be 1. Okay, now we need to differentiate this equation. So if you write differentiate x, this is the differentiation of x. It is the first differentiation of x. It gives you cosine 4t divided by 4 minus sine 4t divided by 4t squared. So let me call this as y, or maybe y1. Okay, differentiation of x. So now I can compute the limit of this y1 at t equal to 0. Okay, and this gives you 0. Yes, the mean actually of the uniform, the mean from -4 to 4, the mean is 0. Okay, if you want to take the second differentiation, you can take the differentiation of y1, or simply you can say y2 x and then comma 2. It means that you take double differentiation of x. This is the double differentiation of x. Now, if you take the limit of y2, it gives you -16 over 3. Okay, so actually one should try it again, because some symbols, when you take the limit, sometimes it gives wrong answers. So this is the reason that I show it here. So don't take the solutions from the symbolic as for granted that is 100% correct. So you need always to think, because now when we take the double differentiation, what it means? The double differentiation means that expectation of x squared. So the expectation of x squared must be positive. It cannot be negative. Okay. Now it gives us minus, so it needs to be go around it again and check it again. Okay. But anyhow, now if we take, let me try one thing more. So if I say y2 equal to differentiation of y1. Yes, it is. Yes, and in this case, yep. Okay, and in this case, if I take limit of y2, there is one problem here, so it must be checked. There are some bugs sometimes. Okay, and if I take the third differentiation is equal to, then it will be the differentiation of y2 or of x 3 times, like this way. Okay, and then I take again the limit maybe I need to define the limit around what? The limit around 0 equal to 0. Okay, then the limit of y3, yes, gives you 0. So the expectation of x cubed is equal to 0, and this is correct. But let us try, what about the limit if this one is the differentiation of y3? So we take the fourth differentiations, then t equal to 0, and then the limit of y4 after the fourth differentiations. Yes, this is correct. 256 divided by 5. Let me go again to calculate the limit of y2, the second differentiation. Yes, now I remember. Now I remember where is the mistake. Yeah, actually, when you take the derivative and you substitute for the expectation, as you can see from the slides or from the lecture, that we should divide by 1 over j or 1 over j squared. Actually, this is correct. This answer that you can see is correct, because we need to divide this over -1, so it becomes 16 over 3. So it is correct. The expectation of x squared equal to 16 over 3. So this answer is correct. I thought that there might be bug, but there's no bug. Actually, it is correct. It is minus 16 over 3, because we need to divide over -1, and then this minus will cancel the minus, then we will have 16 over 3. So you can see that this code or this software gives a great help for you to evaluate the simple calculations when you need them. So always try to use them in your research, in your in your courses. Try to be familiar with these simple calculations in Octave, but still you need to use your mind all the time. Think all the time. Think about the result. So now when I take the y squared, when I take the differentiation 2 times and I take the limit at t equal to 0, it gives me minus. Then I need to stop here. Expectation of x squared must be positive. Why it gives minus? Then there should be some mistake here. There should be some error here. Okay, either the error bug in the code, or error in the system, or error in my understanding. So there must be something wrong. I cannot accept that expectation of x squared to be negative number. But now I remember that I forget to divide by -1, because we need to divide by -1 here in order to get the expectation x squared. I show you where this will be. I will stop this sharing and I will share again the share. Yes. So you can see here, if I go back to the expectations, you can see the concept of the mean. Yes. So the expectation of x of the power I equal to the differentiation of the characteristic function, and here you divide by j of the power I. Okay, so now I equal to 2, so j squared equal to what? J squared equal to -1, because it's square root of -1, so j squared will be -1. Then I need to divide by -1, then that minus 16 over 3 becomes 16 over 3. So we should always remember and know how to make these calculations. Okay, so if we go back to the quiz now. Yeah. So this is the first part of the quiz. The second part, they say that two independent random variables, x1 and x2, where x1 has exponential probability distribution with lambda 1 equal to 1, and x2 is zero mean normal distribution with sigma square equal to 4. Find the characteristic function of random variable y, and random variable y was given like 5x1 plus x2. Okay, 5x1 plus x2. So if we go back now to our characteristic function of each one. So you can see here, actually it was given already, for the exponential distribution. I think it is given somewhere here in one of the examples. Yes, it is here. You can see this is the characteristic function in case of let me just open the pencil. Okay. Yeah. So you can see this one is the characteristic function when lambda equal to 1, it becomes 1 minus divided by 1 minus j t. That's all. This is for x1. Okay. And now if we go to what is the characteristic function of the exponential for the normal distribution, this one. This is for the normal distribution. Okay. So now for the normal distribution, you will have mu. It was given that zero mean. Zero mean, so this number is 0. So it becomes that E minus sigma squared was given as 4. So it will be 4 divided by 2 is 2. So it becomes minus t squared. This is for x2. Okay. So, and in general, so to find the distribution for any, for example, if you have this normal distribution was x1, okay, or the exponential distribution, and we have 5x1. Okay, we have 5x1. What is the now you can call this one, for example, like z, for example. Now I want to find the characteristic function of z. Okay, so the characteristic function of z, phi z, equal to what? Equal to the expectation of E. It becomes j z t. Okay, so z here will be 5x1. And then you take this over let me go to the whiteboard. Becomes easier. Yes. So now we have, let's say we have z equal to, for example, 5x1. We have the distribution of x1 is equal to E minus x1. Okay. So the expectation of E about j z t equal to the integration from 0 up to infinity becomes E j 5 z is 5x1, okay, t times E minus x1, then we have here d x1. Okay, then the integration becomes as we have integration from 0 up to infinity, E of j5 t. I am trying to solve it step by step, so it is good also for you to remember how to do these calculations. Then it becomes minus 1. Okay, then multiplied by x1, or you can take the negative sign outside. Then we have here minus, and we have here plus the x1. So then when you take this integration from 0 to infinity, so of course the integration of e to the power anything, it will be 1 divided by 1 minus j5 t. Okay, then of course, then you take this from 0 to infinity, this will be 1. So this will be the result of the integration. So actually, the difference will be that you will have here 5. You will have, instead of using minus jt, it becomes minus j5t. And then we want to find y equal to 5x1 plus x2. And we know that when we have this summation, then the characteristic function will be the multiplication, because the resultant probability density function will be the convolution between those two. And we said that the convolution is usually is hard to find, to evaluate, but it is easier to use the characteristic function. So phi y of t will be phi z of t multiplied by phi x2 of t. We know this one is this one, so it becomes 1 divided by 1 minus j5t multiplied by phi x1 is e minus 2t. That's it. So this will be the characteristic function of y. Then in the second part of the same question, I asked that what will be the probability density function of y without solving. I said without solving the problem, then the probability density function of y equal to the integration. It is the inverse Fourier transform. The inverse Fourier transform. So it becomes from the integration of y from minus infinity up to infinity, 1 divided by 1 minus j5t multiplied by e minus 2t multiplied by e minus j y t, then dt. So when you solve this equation, if it is possible to solve, me myself also, I didn't try to solve it. Most likely that it doesn't have closed form solution. But if you solve this one, then you will have, or you will find the probability density function of y. Of course, many times that even when we have such kind of differentiation or integration that we don't know the closed form solution to find the final solution, then but it is possible also to approximate this solution by using linear or using numerical integration. So by using a numerical integration, we can approximate the solution, and then we can approximate what will be the shape of the distribution of y. Okay. And the final question in the quiz. Yes. Not this one. So for a random variable y equal to alpha divided by x, it is very similar to the quiz that we solved it last week. But now I added another parameter, alpha. And this alpha, we said that it can take two values that yeah. So it can take two values, as you can see, -4 and 6, and with the probability 0.3 and with the probability 0.7, and we need to find what is the expected value of y. So in this case, I try to do it here. Okay. Yeah. So in this case, we have like expected value of y equal to the expected value of alpha divided by x. Okay. And then, of course, here alpha, it has two values, either -4 or 6. So in this case, to take the average, we can divide the problem into two parts. We fix alpha, so it becomes like expected value of 1 over x when alpha equal to -4, or here is alpha here, when alpha equal to 0.4 times the probability that alpha equal to -4 plus the expected value. I take the average over these two values, alpha divided by x, when alpha, because alpha takes two values, equal to 6, times probability that alpha equal to 6. So this will be expected value. Of course, alpha equal to -4, you can take this -4 outside, because when we fix alpha at -4, that means now alpha is not a random variable anymore. So we determine for certain alpha. So we can take it outside the expectation. So it becomes -4 expected value of 1 divided by x okay, times probability alpha equal to -4 is given as 0.3, so times 0.3, okay, plus, again, when alpha equal to 6, we can take it outside the expectation, so it becomes x 6 expectation of 1 over x, okay, times probability that alpha equal to 6 is 0.7, so it becomes multiplied by 0.7. Okay, so what is the expectation of 1 over x if x is uniform and from 1 to 2? So the expected value of 1 over x is equal to, actually, I explained this last week, but I will do it again here. So it becomes the integration of from 1 up to 2, 1x multiplied by 1, because it is uniform and the width is 1, so the height is 1. So it becomes dx, and this equal to ln x, or natural logarithm x, from 1 up to 2. Of course, the natural logarithm x of 2 is equal to ln 2, and ln 1 equal to 0. So this will be natural logarithm of 2. Okay, then we can substitute this here, this equation. Then we will have like ln 2 multiplied by -4 times 0.3. I don't have close calculator here, but by it will be 0.3 times 4, okay, plus 6 times 0.7. I think it will be around 3. So this should be around 3, something like that. So this will be the mean of the uniform, or for this random variable. Actually, it will be very helpful for you if you try to repeat the same even today after this lecture. Try to do it with Octave. So how could you generate this random numbers? You can generate x as a random number from 1 to 2, random x from 1 to 2. Because it is from 1 to 2, you have to add 1, so it becomes from 1 to 2. And then you generate this alpha as a random numbers, okay, which can be -4 or 6 with the probability, -4 with the probability 30% and 6 with the probability 70%. Okay, then divide them together, then try to find the expected value. Try to just take the mean, and you can find the result. Actually, I think I added this to the new version of the book. I believe that I added somewhere, also with the code itself. So this one. There is now more than 70 solved example in this chapter. So I hope that you will have time to study all these examples. So more than 70 or 80 examples, solved example with software. So all of them, you should try to do all of them. And if you have any questions about any example which is not clear, not like you didn't understand anything in the example, so we can discuss this in the either in the lecture or in the weeks, because as I said, I will reserve 1 week for reviewing and for going through the whole course again. So when you try to solve all the examples, and if you have any questions, just ask me in that week. So you can see that many solved examples. Actually, this is the procedure that I used in this book, that learning by examples. So I give just the concept without going into the details of derivations of equations. You can see that if you go to other books in probability theory, you will find a lot of derivations. Here I try to avoid going in the details of any derivations, but I focus here about the understanding over examples. So I give the concept, and after that I go to this one actually. Example 50, you can see it here. It is the same problem that you have in the quiz. For a random variable y equal to alpha divided by x, and this is the same, so you can see it gives 3 ln 2, and then this is the code. This is the code to do it. But please, before you study the code, try to write the code yourself. This is a very important way of learning. So before you look to the solution, try first yourself to solve the problem without looking to the solution. After that, if you fail, you can then study how the solution has been done. If you don't understand, ask me or ask Dr. Farhad. Okay, and then you come to the code. Don't look to the code. Try to code it yourself. Okay, try to code it yourself. How could I use Monte Carlo simulation to find the mean of this problem? Okay, then if you couldn't, or if you have like a lot of bugs in your code, then you can ask, and also then you can study how did we perform the code to solve the problem. Okay, so this is very important in the to study and to learn from this course. Yep. Any questions about the quiz? Okay, good. Now we come back to the rest of our lecture, where we talk about the random process. Let us go to the أيوة. Yes.
أنا ممكن عندي سؤال بس
Yes. You can ask. ممكن تسألي. ما فيش صوت. Okay, now let us go back to the topic of the lecture today, which is related to the stochastic process and how to evaluate the randomness of in time series or in stochastic process or random process. Okay, so in last lecture we talked about 3 kinds of processes, and we said that we have the general process, which is can be non-stationary, and then we talked about stationary process, and we said that we have 2 kinds of stationary process, that's stationary in the wide sense and stationary in the strict sense. And we said that the stationarity in strict sense, it means that all moments are not function in time, and then in the stationarity in the sense of mean and the variance or the autocorrelation, then we have this is as a special case. Okay, so we have talked about this. Yeah, so we can see here that the random process, this is in general way. So in general that we will have the time to be there in our calculations of the mean and as well as the correlation. We said that we don't have or to measure the scattering of the signal or the randomness of the signal, we need to calculate what is known as the correlation function or the autocorrelation function. And the autocorrelation is given, as you can see, the expected value of the random process at T1 and times the random process at T2, as you can see. And this will be calculated in this way in the general form. Okay, and then we defined also the autocovariance. The autocovariance of a random process is given by this way: the covariance between x and x at T1 and at T2. It gives us the autocorrelation between T1 and T2 minus the expected value at T1 times the expected value of x at T2, and we call this as autocovariance function. And if any of the mean at any of the time is equal to 0, in that case, the autocovariance is the same as the autocorrelation, because the mean will be 0. After that, we took this example that we have a random process, which is like changing between +1 and -1, but it changes with time. So the probability of getting +1 is equal to 1 plus k divided by 1 plus 2k. And of course, the probability of to get -1 will be 1 minus this value, because the total probability must be 1. And in this case, we got that this is the probability of being -1. Then when we keep what is the mean of this process, so you can see that the mean is function in k. K here is the time, actually. K here is the time, but in discrete time, or the iteration, the number of iterations. So it is the time factor here. Okay, so you can see that when you start in the beginning at k equal to 0, the mean of x equal to 1, but as k increases, the mean of x is decreasing until it reaches to 0. When k becomes infinity, 1 divided by infinity equal to 0. And also the power of the signal, or the autocorrelation of the signal between k and k, it gives us 1. So this is the autocorrelation of the signal at the same time at m equal to k. Okay, and at autocorrelation between different time, so it is 1 plus 2k times 1 plus 2m at iteration k at iteration m, where k does not equal to m, when k does not equal to m. So actually, this is very important to remember that when you want to evaluate any autocorrelation function between at t1 and t2, or between k and m, remember that to evaluate them separately. So you need to evaluate this. For example, first at k and k, you can evaluate it at k and k, or at t and t. So it is evaluated first, and then you evaluate at when m does not equal to k. Because if evaluated at m does not equal to k, it gives you this one. So now, if you say that m equal to k, it gives you 1 divided by 1 plus 2k squared. And this is not correct. This is not correct at m equal to k. So at m equal to k, you need to evaluate it separately. First, evaluate at k and k, then you can make the evaluation at different time instances. For example, here, k and m. And also the covariance of x between k and m, it gives us this value. So you can see here the covariance when k goes to infinity, it becomes 1 divided by infinity, so it will be 0. So the covariance goes to 1. Okay, and in the beginning, at k equal to 0, for example, at k equal to 0, so it will be the covariance in the beginning equal to 0. And this is actually accepted because in the beginning we have only one point. So the covariance of one point equal to 0 because you are in the same place. Okay, but as you are like moving in time, so the covariance will increase until it reaches to 1. Okay, then we have here some simulation that we did for the example. Okay, so then we talk about, as I said, about the stationarity. So stationary process. So stationary process actually will simplify the analysis, because it will be difficult that if your mean and correlation all the time depending on the time. So if it depends on what time you take the mean, and it depends on what time you start to look to the correlation, the process becomes very complicated to analyze. And then we define what is the stationarity. So the stationarity means that the mean of, as I said, that the stationarity in the strict sense, okay, it means that the mean and variance and correlation and every moment is not function in time, as you can see. Every moment is not function of time. Why? Because the distribution, the probability density function of the random process x, which should be x and t, as you can see. But if there is no t here, so if it is not function in t, what it means? It means that this random process is stationary in the strict sense. So, for example, if you compute the mean is not function in time. If you compute the correlation, so you can see the correlation is not function in at what instant of time you take the correlation. It is function only in the time difference in the process. So I am only interested T2 minus T1. So I am not interested where is T1. So we are looking only to the difference in the time. So this is called stationary in the wide sense. And actually, stationarity in wide sense is enough for us in electrical engineering, or in wireless communication, or in communication in general. It is enough for us, because usually in our signals we deal with the signal strength, for example voltage or current, and we deal with the signal power. Okay, and those two things is the first and the second moment. So in telecommunication, for our application, the stationarity in wide sense is enough for us to make our calculations much easier. So now when you take the mean of x of t, it will be mu x. So it doesn't matter. So if you take the mean of the signal today, it will be mu x. If you start to take the signal today, the mean of the signal today, but in the afternoon, it will be mu x. If you come tomorrow and you take the mean, it will be mu x. If you come after 1 year to take the mean of this signal, it will be still mu x. So in that case, we call this signal is stationary. The signal is stationary. It is like, for example, white noise. White noise is completely random signal, but the mean is zero. The mean is zero today or tomorrow or before 1,000 years or after 1,000 years. The mean is zero. It is not depending on the day. It doesn't depend on the time. Okay, so we call that the stationarity in the mean. And also, if you, for example, and I gave one example last week when we talk about, for example, the temperature in days. We said that the average temperature is not stationary. Is not stationary. For example, if you say the average temperature in May in Benghazi is not the same as the average temperature in for example in June, sorry, in January or in February, for example. So that the average temperature is not the same. The average temperature depends on the month that you take the temperature. Okay, in that case, we call it that non-stationary process on the long run. Okay, and also compared with the distance or with the location, the average temperature is not the same. For example, the average temperature in now we are in December, so the average temperature in December in Benghazi, it might be like plus 10, okay, and the average temperature in Helsinki is minus 10. Why? They are not the same. So it is also depending on the location. So it is not stationary in the location. It is not stationary in time. Okay, but in signals they are stationary, at least in some applications that we are interested in when we talk deal with noise, when we deal with some signals. So it is important to have this concept. Also, if you take the average, for example, within December month. For example, today, the average of the 3rd day of December, and the average of the 4th day of December, and the average of the 5th day of December, we might assume that they are stationary when we reduce the time. So we say that it is stationary within this small time, but it is not stationary over the large time. So you can put this assumption. Of course, it is changing, but it's changing very slowly. Okay, and this concept is important in wireless communication, because in wireless communication, the channel itself is non-stationary. The channel, but if you look to the channel within the time duration of the symbol, we can assume that it is stationary, because within very short time, the channel, we can assume that it has not changed, or it is changing in the block way. Okay, so it is stationary in the short term, stationary. Okay, so those concepts are important in our research. Then if we continue, then we talked last week also about the ergodic process, and we said that the ergodic process, it says that if you take only one time realization about the random process, and you take the mean and the variance or the correlation of that single time realization, it gives you all the statistical properties of the process, of the whole process. What I mean, if you take the white noise, the noise, for example, of shot noise or thermal noise, and you take record for this normal noise, let's say for 10 minutes, Okay, out of this 10 minutes, you compute the mean and the variance. Okay, then this mean and variance of this white noise, if you can say that this is the real mean and this is the real variance, that if you take even 100 year of measurement, it will be the same mean and the same variance. If you come tomorrow, or if you take the white noise from in this resistor or in that resistor or in any other resistor, it will have the same statistics. The same statistics. So now we need to think differently, that we are not talking about the real signal. The real signal or the actual signal is random. The actual signal is random. Let me, even I don't like to write over the PDF because it makes problems, but I just show something. So if we talk about the signal, so the signal will never be the same. The signals, the probability that you have different signals to be the same is equal to 0. So there is no signals they are like each other. But what the ergodic mean? The ergodic mean, the statistics of this signal is the same. So the mean of this signal is the same as the mean of the second signal is the mean for any other signal at any other time. The correlation characteristics of the signal is the same. Okay, in that case, we call this signal is ergodic. So if we take one-time realization of the signal, and we compute the mean and the correlation, and we can say that this mean and correlation of this single realization is the same as any other signal mean and correlation from the same source or different source. For example, you are talking about thermal noise. So it doesn't matter that in what conductor that you are looking for the noise. So the mean and variance will be the same as far as you have the same resistance, for example. Then we call this as ergodic. So when you take measurements over one time realization, it gives you all statistics of the original process. So in that case, we call this as ergodic. Ergodicity actually has simplified the analysis a lot. So we have, for example, we say ergodic in mean or ergodic in correlation and so on. So when we talk about ergodic process, we can compute the mean over time. So the mean will be 1 over t integration from minus t over 2 up to t over 2 x of t dt. So you can see now we don't have the probability density function anymore. We don't have the probability density function anymore. But this is valid. Remember, you should differentiate between a random variable and a random process. Now we have a random process. We have a random signal which is varying with time. Okay. Now we don't have the probability density function. We can take the average over time. Is this always true? No, it is not always true. It is true only if the process is ergodic. If the process is ergodic process, then we can say that the mean of the over time, or the correlation over time, is the same as the mean and correlation over the probability density function. So the original way, which or the function which save or which contain all the fluctuations and the statistics of any random process, is the probability density function. However, this way of calculation will simplify the analysis. So taking one-time realization, when t is large enough, when t is large enough, then we can extract the statistical information like mean and autocorrelation function or cross-correlation function or any parameters. Then also in the previous lecture, we talked about the autocorrelation function, Rxx of tau. And we said that if Rxx of tau is wide in time, because it is function in time, it is function in the delay tau. If it is wide in time, it means that the randomness of this signal is small. Okay, so it is good to or it is possible to predict the future or to make the interpolation if the correlation is large. So you can see now the correlation in this way is large enough, so you can see this is the time changes of the signal. So yes, there is randomness, as you can see, it is random, but still this randomness is changing slowly. And if you take the signal at any time, so it is still highly correlated after some time tau. So it is highly correlated. So we have high correlation in this signal. On the other side, if we go to some signal that which is much lower correlation, for example, this is the uncorrelated random signal. You can see how will be the correlation. There is actually no correlation. The signal is only correlated with itself. Okay, so at the same time, when tau equal to 0. Otherwise, if you go away from tau equal to 0, you have such kind of large, very high randomness in this signal, very high fluctuations. It means that if you are at any time instant, you will not be able to predict what will be the signal after even 1 microsecond, because it fluctuates very, 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 very fast. Okay, the fast fluctuations means that high randomness in this signal. High randomness means lower correlation. This is the reason that when I said the autocorrelation is the way of measuring the randomness of the signal, and it is equivalent to the scattering of using variance in random variable. Okay. Then we need to talk about one important topic, is the energy and power spectral density. Okay, so what is energy signal and power signal? It is some basic thing, but we need to go through it. So let me to the whiteboard. Yes. Yes, so you can see here that if we have this signal, this is signal maybe E minus alpha t with time t, and at t equal to 0, this thing start with 1, and then it will go to 0. Okay, so this signal has finite energy. Why? Do you remember what is the energy? The energy is the power times time, or in general form, if the signal is x of t, okay, the energy of the contains in this signal is the integration x squared t dt from depends on the time where the signal is. So that the signal here is from 0 to infinity. So from 0 to infinity. Okay, so the energy in this signal will be the integration from 0 to infinity. X squared will be 2e minus 2 alpha t dt, and this will be minus 1 divided by 2 alpha e minus 2 alpha t. The integration limit from 0 up to infinity. At infinity equal to minus 1, equal to 0, and minus at 0 equal to 1. So it will be minus 1. So the result will be 1 divided by 2 alpha. So the energy in this signal is 1 divided by 2 alpha. Okay, so this signal, we call it like energy signal. The signal is energy signal. Okay, let me take another signal as energy signal. So if you have one pulse in this way, okay, and this pulse has amplitude, let's say 2 volt, and it is in the time, it starts at 1 second, and it is ended at 5 seconds. Okay, so now this signal is also energy signal. Why? Because it has finite energy. Since it has finite energy, so we call it as energy signal. And if you want to compute the energy, of course, now we talk about like normalized energy, because if you we assume that the impedance or the resistance equal to 1, so it is called normalized energy. So the normalized energy here, it will be 2 squared, it will be 4, okay, divided by r, but we assumed here the r is equal to 1, v squared divided by r, and then it is multiplied by time. So the time here is 4 seconds, so it will be multiplied by 4. Okay, so if it is given in second or in hour or whatever that unit that you want to use. So the energy here is 16. It gives your energy is 16, like what time is seconds. Okay, so now this is the energy, finite energy. So those signals, we call them that those signals they call energy signal. Okay, but we have another signals. For example, if you have sine wave and it is not defined to infinity, or if you have like random signal, like voice signal or whatever, and it continues to infinity, so they are not limited in time, as you can see, both of them. So in this case, the energy contains of this signal will be infinity. The energy equal to infinity, and here the energy equal to infinity, because it is not defined in time. Of course, if we take just at certain time, we call it in this case like energy signal, because it will be finite. But if the time is not defined, then we have infinity energy. In that case, we need to take certain period of the signal, is t, for example, and we look to certain period of the signal at t, and in this case we call it like power signal. Power signal. In the power signal, the power contains in the signal, we need to specify the time. So we take the limit, okay, but we need to define over some time integration from minus t over 2 up to t over 2, or from 0 to t, it doesn't matter, it is the same. Then x square of t dt. Of course, we can take the time even up to infinity, but you can see now you define over time. Since you define over time, so as the time increase, yes, this x squared will increase, but also t will increase, which means that the signal will be always limited. The signal will be limited, and if the signal is limited, we call it as power signal. Okay. Now, our random signal or random process like voice signal or image signal or noise signal, maybe channel fluctuations, whatever was the signal is, usually it is power signal. Usually they are power signal. So usually this random is power signal. Okay. The random process usually changing in time, but in wireless communication or telecommunication, in power systems, in almost in every branch, it is very important to explore the frequency contents of this signal. What are the frequency contents in that signal? Okay, what are the frequency contents in that signal? Why we need this? For example, if I want to design my communication system and I want to send like the minimum required bandwidth, which contains all information of voice. If I asked you a question now, I asked you that design like communication system, digital communication system, and to send the human voice. Okay, so we have, for example, a speaker here, a microphone here, and then we will have like low pass filter or band pass filter. Then of course you need to have sampling and electrodigital converter. Okay, and then you have the quantization. Okay, and so and blah blah blah. Okay, so now we know that in wireless communication the spectrum is very scarce. It is very valuable, the spectrum. So we shouldn't use any spectrum more than needed. So the question now, what is the minimum bandwidth, okay, that we need in order to carry the voice information? The voice information. Okay. Then you asked me what I mean by minimum required. I told you the minimum required that the voice should be understandable. Okay, so the listener should understand what the speaker says. This is the first thing. And the second thing, I need to the listener to understand who is speaking, or who the speaker is. So it means that it should contain that clear, the phonetics should be clear, and also the thumb of the voice, or the like the feature of the speaker. So they should be known as well. So you should be able to recognize who is the speaker, and also to understand the words. So in that case, maybe I need to, for the voice spectrum, we know that the voice spectrum for the human is between about 20 hertz, for example, up to like 15 kilohertz. Okay, so now I don't need to use all the spectrum. Maybe the all spectrum is good if you want to send music, for example. But for the human voice, we don't need to send most of this spectrum. So I need the spectrum where I can send 90% of the possibilities or probabilities of the changes of the signal will be there, or 90% of the energy of the signal based on the spectrum, based on the frequency domain. In order to solve this problem, I need to convert this random signal into frequency domain. Okay, into frequency domain. This is in a frequency domain. So in a frequency domain, because this signal is powered signal, the energy is infinity. So we need to take some time sample for that, and then this we need what is known as power spectral density. Power spectral density. Okay, so now we have this signal x in time. This is x of t. Okay, and then we have the same signal in the frequency, x of f. Okay, now I need 90% of the signal. Then I can say that what is the 90%? Maybe I can find that the 90% of the signal will be from this f1 up to f2. Actually, in wireless communication, it has been, or for a human voice, 4 kilohertz contains more than or around 90% of the information of the voice. So you don't need to send all these 15 kilohertz, only 4 kilohertz is enough. But how could we reach to this conclusion? We need to convert the signal from time domain to frequency domain. But there is a challenge here. What is the challenge? For example, if I told you that x of t is some signal like, for example, maybe e minus t, and I asked you to find the frequency domain of the signal, it is very easy because x of f equal to the Fourier transform integration from 0 to infinity, because this t is defined only greater than or equal to 0, from 0 to infinity. Then we have x of t times e minus j2 by ft, as you remember, dt. When you make this integration, you will get the frequency domain of the signal. However, in random process, in our random process, x of t is random. We don't have equation for x of t. We don't have equation. X of t here is a random signal. Every speaker, when he speaks, he generates some signal, and this signal is random. This random, it means that it doesn't have, or we cannot put it in equation. There is no equations that can represent this signal as in deterministic way, because it is a random signal. Okay, now how could I find the frequency content of this the frequency contents of this signal? Okay, so before I go to that to solve this challenge, I show that the total energy in of the signal in time domain and the frequency domain, of course, is the same, because it is the same signal. X of t, if you convert it to frequency domain, it becomes x of f. But they are the same signal. It is like that you are looking to you in the mirror. So it is the same. The same signal is x of t, but it is another domain. It becomes x of f. So the total energy of the signal in x of t will be as the same as total energy of the signal in x of f. Or the total power, or the average power of the signal in xt is the same as average power of the signal in xf. Okay, so in general, you can say that the integration from minus infinity up to infinity, x of t square dx should be the same as the integration of the all frequency from minus infinity to infinity, the absolute of x of f square df. They should be the same energy. Okay, however, this one, the absolute value of x of f, is called the power spectral density of the signal. So this is general. The absolute value of x of f square is the power spectral density. What is the power spectral density? It gives you how is the energy of the signal, or the average power of the signal, distributed over frequency. For example, if you have something like that, and then we have, let's say this is 10 hertz, 20, 30, 40, 50, and so on. So if I give you, this is the absolute value of x of f square, so you know that most of the energy of this signal is distributed within these two frequencies. It is from 20 hertz up to 40 hertz. You have 60 or 70% of the total energy. of this signal. So it gives you such kind of important information. How is the energy of the signal distributed over frequency? Over frequency. So this is very important in telecommunication and also in power systems. For example, when they try to like recognize where is the fault, if there's some fault happened in the power system, and then this fault, usually we can track it by converting the signal, the Fourier transform of the signal, taking the frequency domain of the signal, and then by looking to the harmonics of the signal, we can determine with some accuracy, of course, not 100% accuracy, but we can guess where should be the fault and where it happened. Okay, so the frequency contains or the frequency information of the signal is very, very important. However, again, now I come back to the same challenge. How could we find this one? How could we find x of f? The signal itself is random. So how could we find the averaging of x of f? Of course, here it means that it is average, you know. It is averaging. So if you take the signal every time, you might have a slightly different shape, but this is the average. So this curve gives you the average changes of the signal with the like energy with the frequencies. So the power spectral density or energy spectral density is very, very important. Power spectral density is sometimes called energy spectral density. Okay, they are very important in stochastic process or in random process. Okay, the derivation was already given in the book and in the distributed chapter, but I will not repeat it again here. It is very easy to do it, but even you don't, it is, I advise you to study how is the derivation, but don't worry that if you cannot do it yourself, but you should be able to do it yourself, but don't worry about that. The concept here, that to know the frequency transform or the Fourier transform of the autocorrelation function Rxx of tau. Okay, it gives us the power spectral density. It gives us the power spectral density. This is the absolute value of sorry. Okay. So this, if you take the Fourier transform Rxx of tau, if you take the Fourier transform of this one, it gives you the power spectral density or the energy spectral density. It depends on the original signal itself. So it gives you, in other words, the averaging of absolute value of x of f square. Actually, this is very important result. So this shows us that when you take the autocorrelation function, when you find the autocorrelation function for the ergodic, actually the derivation in the book was given for the ergodic case, but the result is valid for any other random process, stationary, non-stationary, or ergodic. The Fourier transform of the autocorrelation function, it gives us the power spectral density. So this is very important result. Let us go back to the chapter. Okay. So you can see that what I explained on the whiteboard. Yes. So this is called as I said, power spectral density. As you can see it, phi of f equal to the absolute value of x of f squared. And after that, I explained a little bit the difference between time limited. This is now when the power signal, the average power, we take over average power. Okay, I explained this already. Okay, and now if you take the Fourier transform of Rxx of tau, it gives us, just you substitute here, Rxx of tau times e minus j2 pi ft. It is just the Fourier transform. Okay, and now what is Rxx of tau if we are ergodic? In ergodic signal, Rxx of tau is given here. For ergodic signal, Rxx of tau, this is Rxx of tau. for ergodic signal. So it is just the averaging of the signal over 2 time instances delayed by tau, and it is the average in time domain, the average in time domain. This is valid if and only if the signal is ergodic. Always you remember that, this way of finding the autocorrelation. However, we are always using it. In wireless communication, we are mostly assume that it is ergodic. And this assumption of ergodicity is valid when we talk about very small symbol transmission. If the symbol transmission is very small, is much lower than the coherence time of the channel, it is valid to say that it is ergodic process anyhow. So now you can take this Rxx of tau, and you can see that this is the equation. So I substitute by Rxx of tau, I substitute with this integration, and then we got it here. So you can see I just substitute x of t times x of t minus tau, and actually the exponential here is function in tau. This is the reason that I separated the integration over 2 different integration. The first integration multiplied by this one, so it is only in tau, and then the second integration with respect to t. We know that the time shift, the Fourier transform of the time shift will be x of f, but multiplied by e of the power of this time shift, as you can see, and then taking the integration. As I said that if you didn't understand the derivation, which should be easy for you, but if you don't understand it very well, it doesn't matter. So the important result here is that the Fourier transform of Rxx of tau is the power spectral density. It gives us the power spectral density. This is very important. And also it is important to remember that even the derivation or the proof was given for ergodic signals, but the result is valid also for non-ergodic and non-stationary random signals. So the result will be valid for both of them. The only difference will be that here we have this the power spectral density, this one. But if the signal is non-ergodic or it is non-stationary, you will need to add the time information here, where you take this time. So the time information will be important. It is still the same. So as you can see that you take the Fourier transform of the autocorrelation function, but if the signal is stationary, we say that Rxx of tau, because it will not make any difference if you know at what time you are now. But if it is non-stationary, then we need to take it for our xxt and tau. It is important where, at what time, in which month you take this autocorrelation. Is it in April, or is it in May, or is it in December? It makes difference. If you add this time information t, where you take the measurement, it will appear also here. This is the main difference between the non-stationary or ergodic cases. So, but the concept is the same. The concept is the same, and actually it can be also approved, the concept, but it can be a little bit more complicated. And this will be the how to find the autocorrelation function or the power spectral density from the autocorrelation function in case of non-stationary process. But it is a little bit more complicated than the ergodic process. After that, we gave one example. Assume zero mean random process x of t with autocorrelation function. So the autocorrelation is given in this way. Then they ask it, is this process stationary? Of course it is stationary. Why? Because we don't have the t information. We have only the delay information. Because now we have autocorrelation means that expectation of x at t times x at t plus or minus tau. Okay, plus or minus tau. This way. If there is no t information here, so you cannot see any t, we have only the delay tau, then this process is stationary. What is the power spectral density of x of t? The power spectral density is the Fourier transform. Is the Fourier transform of this Rx of t. It gives you the power spectral density. Okay, and then what is the average power of x of t? We will see how to find the average power of x of t. Actually, the average power of x of t is the same at tau equal to 0. So when you take tau equal to 0 here, what happens if you take tau equal to 0? It becomes expected value of x of t times x of t. And this will be expected value of x squared of t. So this is the average power of the signal. So the average power is simply at our xx at tau equal to 0. So if you put here tau equal to 0, the average power will be 2. Okay. The fourth requirement here, if we aim to design an ideal low-pass filter that allows 90% of the average power of this process to pass through, what is the bandwidth we should use? This is very interesting question here. So now we have the Bose-Packer density, that it is a Fourier transform of the autocorrelation function. So we have the Bose-Packer density, okay, and then we are looking for the bandwidth which contains 90% of the average power. So we know the average power. The average power is when substitute tau equal to 0. So it gives you 2 watt. Okay, 90%, it will be 0.9 times 2. So it will be 1.8 watt. So what we need to do here, we need to integrate this power spectral density from the bandwidth, for example, from minus f0 up to f0, okay, df, which gives us 1.8. So now we can find the spectrum that contains 1.8 watt. And this was given, as you can see here, we show how to calculate or how to compute or to find the Bose-Packer density. It is the Fourier transform, and we solve for the Fourier transform. Please, when you study, for example, at home or in a group, when you study the examples here, for example, if you didn't understand why I separate this into two, just make a remark here. Put your remark, and when we come to the review lecture, you can ask me. You can ask me about every example that if you don't understand. However, this should be calculus, actually. This should be integration, because here we have the absolute value, and you know that the absolute value of x, okay, equal to minus x for x less than 0, and equal to x for x greater than or equal to 0. Because the absolute value, if x equal to, for example, minus 5, the absolute of minus 5 equal to 5. So if x less than 0, so if x equal to minus 5, minus minus becomes a plus, so it becomes 5. Anyhow, any questions that you have when you study the examples, you can ask me. Then finally, we find this is the power spectral density of this process. This is the average power, as I explained now. Then what we need to know, they need to know the bandwidth of this power spectral density, which makes the power 1.8 watt, which means that it is 90% of the total power. Now we need to solve this integration. Again, it is calculus, how to find the integration here. Even I show it in details how to find it. So you can, it is by substitution, and you put 2 pi f squared equal to tan theta, and you solve. It is general. Maybe I just remind you about how to find the integration in this case. So integration 1 divided by 1 plus x squared dx. So if you go back to the integration of this equation, you need you can solve it by substitution. So you put x equal to tan another variable theta, then dx equal to, it becomes like secant square theta d theta, and so on. So I show anyhow how to solve this integration in details in this chapter. Okay, so now when we solve for the bandwidth, we find that we need the bandwidth to be around 2 watt, because it is from minus BW up to BW, and the bandwidth equal to 1.0048 watt, which means that only 2 hertz, sorry, 1.0048 hertz, not watts. So only 2 hertz is enough. Only 2 hertz is enough to get 90% of the signal coming from this random process. So this random process, actually, it can be this random process here. It can be, for example, random signal coming from sensor. So you have sensor, you have IoT Internet of Things, and you have sensor here measuring some value, okay, and you need now to build your Zigbee or Bluetooth modulation in order to send this signal. So it is important to know how much bandwidth you need to send this signal. So now by solving this problem, you know that you need only 2 hertz. You need only 2 hertz to send the 90% of the information coming from that sensor. Okay. Another example here, it was given in case I will stop after this example and give you break. So in this example, it is discrete case. It is the same but discrete case. Now we have autocorrelation function for discrete process, and this discrete process, the autocorrelation, it was given in this way. So again, it is clear that it is a stationary process because it is not function in the exact time, but it is function only in the difference between the samples. And because it is discrete, you need to take the Z transform, not the Fourier transform. We need to take the Z transform, or what is known as discrete time Fourier transform. Actually, they are quite the same. So here we call this as Z minus 1 if we took this Z transform. I will not go in the details of linear system now. But anyhow, this is the Bose spectral density that when you use this discrete time, and this what we got as the Bose spectral density as function in alpha. Okay. After that, of course, we use MATLAB or Octave in order to find the Bose spectral density and also to emulate or simulate these results. We will take a break, 15 minutes break. Sorry that today I need to condense a little bit because, as I said, I try to finish the course within 2 lectures more. So this is the reason that we need to go a little bit faster, but without violating the topic. So I am not skipping over the topics. This is the reason that I started by part of the previous lecture. I'm starting because I like to emphasize about the important things in this random process, like stationarity, ergodicity, like non-stationary process, and then the autocorrelation function, and the Fourier transform of autocorrelation gives us the Bose spectral density. The Bose spectral density is the distribution of the power over a frequency of random signals. So all these are very important. After the break, let's say that we say 15-minute break, then we come to study what is white noise, and after that we start to present some of the important dynamics in random processes. Okay, so 15-minute break. We come at 12:05.
شكرا. Thank you very much.
Okay, so after the break, let us start with white noise. So we know that noise is already like there in electronics. For example, if we talk about advanced communication, the receiver, for example, we have 2 main kinds of noise. We have the thermal noise and shock noise. But if we talk about thermal noise a little bit, so let us go to the whiteboard. So if you have any conductor or resistor, for example, okay, and this resistor R, so usually due to the random movements of electrons within the conductor, in order according to thermodynamics. So we have, for example, the ambient temperature. As far as you have ambient temperature is not 0 Kelvin, the absolute 0, then you will have movement of these electrons, and the movement of electrons is random, and when the number of electrons reached one end more than the number of electrons reached to the other end, then we will have voltage drop here. So this voltage drop means that we will have noise across any resistor or any conductor. And it was proved that this noise is Gaussian. It has Gaussian distribution, normal distribution with zero mean, and the average voltage power, the normalized voltage power, is something like about 4 kTBR. And this K is Boltzmann constant. This T is the temperature, the physical temperature of the resistor. Then we have the bandwidth that you are looking at, the bandwidth that of this signal, and R is the resistance value. And of course, it was proved that the maximum power that you can get from this resistor when it is connected to the matched load, and the matched load, it will have the same resistance again, and the average power, or the maximum power that it can be delivered from this noise, is equal to about KTB. And T is the physical temperature, K is Boltzmann constant, and B is the bandwidth. Okay, so the characteristics of this noise, actually, the characteristic of this noise is that it is white noise. What is the meaning of white noise? It means that it contains all frequencies in the bandwidth of interest. So if we go to the frequency, so you can find that it is distributed in this way. So the bandwidth equal to, this is the power spectral density. This is the power spectral density of the noise. Okay, so it is equal to 1, and it is distributed over all frequencies of interests. Of course, it is not going to infinity, but we assume that it is going to infinity. It can, the characteristic of noise is valid up to several hundred gigahertz. Okay, so now we know that the Fourier transform of the autocorrelation function, it gives us the power spectral density in the frequency domain, psi of f. Okay, now psi of f, or this power spectral density, is equal to 1. So what will be the autocorrelation function? The autocorrelation function here will be direct delta. So it will be direct delta. So it is like delta of tau. So this will be Rxx of tau. And this is called that, this is the reason that we call it uncorrelated noise. So the white noise is uncorrelated noise. It has like very wide spectrum in this way. Okay, and also it has the correlation, it is uncorrelated because it has direct delta correlation, which means that it is only correlated with itself in the same time. So if you have any delta greater than 0, then the correlation or the autocorrelation will be 0. Okay, so just let me talk a little bit about this delta, because we will need this delta actually maybe during the next lecture when we talk about linear systems in general. So this delta, as you know, that is very important for system analysis, and it is given basically like that. So if you have, this is in time, and if you have pulse, and this pulse is like this way, so let's say that this is from minus tau over 2 up to tau over 2. So the width here in time is equal to tau, and the magnitude of this signal is equal to 1 over tau. Okay, or it can be 1 over square root actually of tau. Okay, so now what is the average energy in this signal? The average energy will be the magnitude square, which will be 1 over tau, multiplied by the time, so multiplied by tau equal to 1. And this will be true for any tau. So what happens if you make tau smaller? So if when you make tau smaller, then you will get that this will be like this one. But since tau is smaller, so it will be higher in magnitude in this way. So if you make it even more small, so it will be like that. So when tau goes to 0, when tau goes to 0, then the magnitude of this signal, 1 over square root of tau, the magnitude when you take tau goes to 0, this will go to undefined, goes to infinity. So direct delta, actually, it is defined in this way. So it equal to undefined when tau equal to 0, and equal to 0 for tau does not equal to 0. And the integration of tau, of this tau signal, tau square, or tau, if you can take, if you talk about tau itself, so you can, even without this square root, you can consider it. But if you want to take it as a power, then you need to take the square root. Okay, but if you take the tau itself without square, so it becomes like d tau. Okay, and from minus infinity up to infinity, the area must be 1. So the area is always 1. The area is always 1. Okay, so it means that the total energy of this tau, or the total area of this tau, is equal to 1, but it is undefined at tau equal to 0. Actually, even it is called direct delta function, but it is not function. Delta is not function in the strict sense. It is not function in the strict sense, but they call it like direct delta function. Okay. Yes. Dynamic stochastic process. Okay. Now, when we talk about this random process, we saw. Let me go to the again to the whiteboard. Okay. We saw actually if we have a function like y equal to any function of x, and we know what is the distribution of x. This is in a random variable. When we talk in a random variable, okay, and we know what is the distribution of x. So x, it has distribution like fx of x, and then we need to know what is fy of y. This we have showed before in the first part of this course. And also we see several examples either in single random variable or in joint random variables. What is the case if you have a random process? If x is function in time or in space or anything. So now x is changing with time. And we have a relation y equal to as a relation j of x of t. So this will be also yt. What will be, or how will be, the distribution of y, or the characteristics of y if x of t goes through some function? Okay, so in principle, if j is just like mapping, one-to-one mapping, for example, if y of t equal to 5 x of t plus 1. So in this case, actually you can apply the same methods that we applied before. How will be the characteristics of y? So it is easy. For example, the mean of y, expected value of y, equal to 5 times the expected value of x of t plus 1. So the expected value of y of t equal to 5 expected value of x of t plus 1. Okay, so mu y, if x of t was stationary, then y of t will be stationary, because in this case, the mu of y, the mean of y will be 5 mu x plus 1. So it is not function in time. But if x of t is non-stationary, then the expected value of x of t will be mu x of t, because it is non-stationary, and then mu y of t will be like 5 mu x of t plus 1. So it is also non-stationary. So if x is non-stationary, then y of t will be non-stationary as well. Okay, if you want to calculate what is the, let us keep this simple example, yt equal to 5xt plus x of t plus 1. Now you want to calculate what is the correlation of y. Okay, let us do it. This is not in the examples of the book, but we do it here now. So r y of between t1 or t2 minus t1, it will be the expected value of y at t2 times y at t1. Okay, y, we said that y of t equal to 5x of t plus 1. We substitute here, so it becomes like expectation of 5x of t at t2 here, t2 plus 1 times 5x at t1 plus 1. And this will be, you just substitute this inside, so it will be expectation of 5 times 5, 25, x of t2 times x of t1 plus 5x of t2 plus 5x of t1 plus 1. This will be the expectation. I distribute the expectation inside. This will be equal to 25 expected value of x of t2 times x of t1 plus 5 expected value of x of t2, okay, plus 5 expected value of x at t1 plus expected value of 1 is equal to 1. Okay, so you can see now this one is nothing but the autocorrelation of x. So it will be 25 times the rxx between t2 and t1, t2 minus t1, okay, plus 5 times mu x at t2. Now I am talking general. I didn't say that it is about mu, so I put it general. Plus 5 mu x at t1 plus 1. So the autocorrelation of y between t2 and t1 is equal to 25 autocorrelation of x plus 5 times the mean at t2 and the mean at t1. But since the difference in autocorrelation is only in difference t2 minus t1, so it means that it is stationary. So the mean will be the same. So it will be like, you can put just 10 mu x, okay, plus 1, and this will be 25 rxx t2 minus t1 times 25. So actually, this is only for the basic, very basic equation, but general, if you have any mapping, then you can do it in this way. However, observe that this relation means that any change in x, it will be immediately affect y. Okay, what about the past? The past here is not exist. So for example, what is going on in the past is not coming in y. Okay, so but this is actually hard to find real systems that is not depending on the past, because what we have, for example, the changes of the channel or the changes of any random process, actually they are function in time, which can be dynamic system. Actually, the dynamic system, it means that the current output of the system depending on the current input, but also depending on the previous inputs. For example, if you have this circuit, okay, and now you have the input here, and you have R, and you have capacitor C, and now this is your output. Okay, so the output is not depending only on the input, depending on the input and the history of the input, because it is stored here. So we have dynamic system. Okay, we have dynamic system in this case. Okay, so since we have dynamic system, then we have differential equations. We have differential equation. When we have differential equation, it can be represented, for example, just in general, that maybe d square x of t dt square plus maybe a dx of t dt plus b x of t, and this equal to maybe y of t. Okay, so now we have a dynamic system. It means that the output is not depending only on the current input, but depends only also in the history of the input. It can be even more. It can be, for example, d squared x of t plus a dx of t over dt over dt squared plus b x of t plus maybe some value c, and this equal to d squared y of t over dt squared plus something maybe a1 dy of t, and so on. So in this case, we have, of course, here we have linear differential equations. Okay, we know how to solve differential equations in general, but what if x of t now is a random process? How this will affect our analysis? Actually, I decided not to include how to solve such kind of stochastic differential equation, even it is there in chapter 3 or chapter 2 in the book, but I decided to not to include it in this course, because this course should be like basic course or introductory course in the topic, and that this kind of differential equations, stochastic differential equations, when you have x as a random process, it is a little bit more advanced for this course. However, this what I wanted you just to understand, that when you have dynamic system where the output or the observation that we are looking to is not affected only by the input, but affected by the input and some dynamics inside the input. So we might have a system, for example, that we have maybe, if we just keep our discussion in the circuit theory, so we have inductor, maybe a capacitor, we have some things like that, so another like this, maybe we have some resistor here as well. So now the energy is stored as a magnetic field in the inductor and electric field in the capacitor, and those are actually, they don't save any of those energies. Of course, now we talk ideally. However, those resistors also generating noise, so they generate noise, and maybe you have input, the input, and then we are interested to measure the voltage output here. So, and we can see that the voltage output is function in the input, but also is function in the previous situation, like this is I1 and I2 and the initial condition and many other values. Most of, if not all, in real cases, they are dynamic. They depend on the history. It's not just depending on the instantaneous situation. It depends also in the history. Actually, even in social relation, your relation with someone, maybe we can see a situation that someone becomes very, very angry from other guy, for example, other one, because of simple mistake. So you start to think that there should be something before that. So it is like accumulation. So even in human relations, they are not our behavior in human relation is not based on instantaneous like treatment only, but also we have some accumulated like memory about everything. So in physics, in temperature, for example, um, in the weather temperature, you cannot say that if we know the temperature right now, I can say what is next just without taking into account the average temperature or the dynamics of the temperature. So we can say that almost every physical problem or behavior, it has some dynamics. So it depends on the fluctuations, on the history, or the initial conditions, many other things. So in that case, as I said, if we need to deal with a process, a random process, and it has dynamics, then we need to take all the history. And if we need to take all the history, then we have differential equation, we have stochastic differential equation. Fortunately, there is some cases that we can, it is not necessary to take all the history, but it is enough to take the previous, just the previous case, especially in it can be, of course, in discrete or continuous case. In discrete or continuous case. If we take the discrete case, so if we have what is the probability, you know that now if we have a dynamic system, which means that it is changing with time. So we have x at t, now it is discrete, okay? And we have x at t minus 1, we have x at t minus 2 as a discrete case up to xt minus m, maybe up to x at 0. So start by initial condition, and this random number start to dynamics, some changes until it reach at now is x at t. Okay. So generally, the probability that x of t to be less than or equal to any value x at t0, to find it, okay, you need to take into account all history. So this will be this, to take this one, you need to take into account this equal to, okay, that the probability, maybe of course you you need to take all the history so it can take summation, but actually to evaluate this one, we need to know the probability of xt given xt minus 1 and xt minus 2 and xt minus 3 up to x0. You need to know all history in order to evaluate what is x of t. So in order to understand b at xt to be less than, you know that how to solve this one. You take averaging over all these values, okay? But if you take that xt to be less than or equal to x0 given xt minus 1, xt minus 2 up to x0, if this one is equal to probability xt to be less than or equal to x0 given xt minus 1 only. So if they are equal, what it means? It means that only the last time step in this random process will affect x of t. Okay, it will affect x of t. This special case is called Markovian process. It's called Markovian process. But if we say that x of t, x at t less than or equal to x0 equal to the same as x of t less than or equal to 0, and given all the history, it means that they are completely independent. Completely independent. And this assumption, it makes the analysis much easier. But if you apply it in many different problems, you will get wrong result. You will get wrong result because of the strong assumption that you assume that all time instances are independent. So of course you can apply mathematically, you can do it. And when you make simulation, you can get the result by this assumption of independency. But when you compare your result with the real observation, you will find that there's big difference between the simulation or the mathematical analysis and the real situation. Okay, but if you take into consideration the last step, sometimes it helps a lot. So this is called Markovian process. Markovian process or Markov process. So Markovian process is a mathematical foundation, gives us the opportunity to analyze dependency in this way. Okay, is it possible, or do we have such kind of problems? Yes, we have. We have. Um, I will give some few examples here. Okay, so for example, if you have some final destination that you want to reach, let's say this is D1, D2, D3. So you have some final destinations, and you start with, for example, from certain position, and you can move every time like either up or down. Okay, so you can reach here or here, then here or here. So of course it will be very large positions that you can find. Okay, and finally you become in these positions. So at each step, for example, if you are, let's say, in certain point, you are here. Okay, so now the probability for this random walk to be, because I said that you can go either up or down, maybe it is here, so it's better to be here. So you can go here or here only. So in order to find the probability, what is the probability that you will be in B1? This is probability B2, probability B3, probability B4, B5, let's say up to B100, for example. Assume that you have 100 position at certain time t. Okay. Now, if I don't have any information about the last step where I was, and I want to evaluate this problem like independent problem, and if they are equally likely, so the probability to be in each position will be 0.01 to be here, because we have 100 position, 0.01 to be here, 0.01 to be here, 0.01 to be here, up to 1. So the total will be 1. Okay, because I don't have any previous information. But if you use Markovian process, and in the Markovian process, the probability to be here, for example, at position 1, probability that to be at position 1, x equal to 1, given that this is at t, given that at t minus 1, you was, let's say, in position 5. It is impossible, because you are in position 5, and you can go either 6 or 4. You cannot go to the to 1. So in that case, this will be 0. This will be 0. The answer will be 0. Okay. And now you can be like, if it is equally likely, so it will be 0.5 and 0.5. And all others are 0. Okay. So why you got this result? Because you use this Markovian process. Markovian process, I am interested in the last position where I was. Then I can compute the probability. So the uncertainty here becomes much better before, much better than before. Before, if I use just like equally likely, and I assume that probability at, what is the probability that at t I will be in position 1, and I didn't consider all history, of course, will be very bad result. Very bad result. By considering only one time in before, we have improved the result. Okay, if I asked you now, what is the probability that xt equal to 1, given that xt minus 1 equal to 5, and xt minus 2, it was before that, it was, for example, maybe it was 4. Okay, it was 4 before that, for example. So this information will not affect the result. This information in the previous one, what was the previous before the previous, it will not affect, because the most important thing is the last result that I am now. Where is I am now? It will decide where I will be next. So this will be the same as probability of xt equal to 1, given that xt minus 1 equal to 5. It will be the same. Even if you add all history, it will not affect, because at each time I am just looking. It is the most important thing to understand where is the next step, is to know only the current step. Okay, so let us take another example. There is one a game, of course, it is not allowed, but we can, of course, apply it in different other scenarios. We can apply it in more like realistic or more physical scenarios. But if we talk about gambling, so they start the gambling with certain amount of money. For example, they start the gambling with N. Okay, and then when they start with N, they can get more money or lose money. So if they lose, it will go, sorry, it will go to the money to N minus 1. If they lose again, it will go to N minus 2. If they lose $1, for example, every time, it will go N minus 3 until they reach to 0. Then the game is ended. Okay, but if they win, so they can go. Of course, when they are in n-1, they can also win. If they win, it will go to n. From n-2, if they win, they will go to n-1, and so on. And also, if the beginning, the guy was like earn more, so they will go, assume that every game that they will only like earn 1 plus. So it becomes n+1, and it will continue, for example, until we reach to some m. Then it will reach there, the game is ended. Okay, so here we call that absorbing state. So here we have probability is 1. It means that once you lose all money, then you are lost. And here when you get that m amount, then you winner. Okay, so this also is important, because now if you are in any state, for example, if you are here, so what is the probability, if I asked you, what is the probability that you will get n-3? What you need to know the last state. So the last state here, it can be n-2, or it can be n-4, that you can calculate the probability. But what is the probability that you are in n-3, that in next step you will get n? The probability is 0. We don't have this movement, because you need to go only one step here. So this is called, like, this is one explanation of the Markovian process. Okay, another example, for example, if you have on your table, you have 3 boxes. Okay, you have 3 boxes. One book for mathematics, one book for, let's say, languages, and one book is physics. Okay, and every time you select only, you take one book randomly. Okay, you just select one book in a random way, and you read it, and then you put it as a first book. Okay, so now you want to study this random process. If I asked you what is the probability that if you have math, language, physics, okay, what is the probability that after 10 times of selecting box, you can select any one of them randomly, that you will find the physics book to be the first book, for example. So this also is Markov, because it depends on the states. So if you assume, for example, the state of this process, that, for example, the math book. So the math book can be, it can be the first book, it can be the second book, it can be the third book. Okay, if it is the first book, what is the probability that the second round will be the first book again? So it depends that what is the probability that you are interested in math. Okay, now assume that we use different probability to make it more easier for you. So the probability that you come to math book is equal to 0.4. The probability that you use language book is 0.1, and the probability that you use physics book is 0.5, because the total must be 1. Okay, now the math book is in the first book. What is the probability that it will stay to be first book? The probability is that you will select math. So the probability that you select math is 0.4. So the probability that you start with first book and it will stay the first book is 0.4. Okay, what is the probability that the math book will go to be the second book? The probability to go to be second book, it means that you select the language, you study the language, and then you put the language up. So it will be the second book. Or you select the physics and you study the physics and you put it first. So also the math will be the second book if it was the first book. So the probability here, it will go to be second if if you study either language or physics. So they are mutually exclusive. So the total will be 0.6 here. Okay, what is the probability that the math becomes third book from the first round? This probability is 0, because if you take the language book, you will put it up, so it will be the second. And if you take the physics book, it will be up, so it will be the second again. So it cannot be from the first round to be in the third book. Okay, so now assuming that it is the second book. What is the probability that it will be the first book? It means that the probability to be the first book, it means that you was interested in math again, so you study the math, so it will be in this way. Okay, and so on. So I mean here that by using this transition cases, we call this as Markov process. So Markov process, we call if each problem as a state, and then the transition from state to state is called transition probability. This is called transition probability. So if I go to the book, so you can see here that yeah. So this is the Markov process, and then the probability for the state to move from I state to J state is called Bij, as we show now when we say that if you are 1 and here we have 2 and here we have 3 states. So from 1 to 1 is called B11. From 1 to 2 is called B12. From 2 to 3 is called B23. And from 3 to 3 is called B33, and so on. From 3 to 2, it's called B32. So the first state, where are you now, and where you will be in the next like iteration, or in the next transition. This is called probability Bij. Okay. So since they are a probability, so as we know that the probabilities must be greater than or equal to 0. So Bij must be greater than or equal to 0 for all Ij. And also the summation of Bij from any like from any state to the other state, the total probabilities out from that state must be 1. Must be 1. Okay? It means that the total row, the summation of each row must be 1. This is called the probability transition matrix. This is called probability transition matrix, as you can see. So we have here states. We will see several examples actually explaining the concept here. So we are 0. We are in state 0. So coming and returning to the same state is called B00. And from 0 to 1 is B01. And from 0 to 2 is B02. Remember, the total probability must be 1. Means that B00 plus B01 plus B02 must be 1. Because if you are in state now, and now you move from that state. Once you move from the state, then you have to move to one of the other states. Either you return to the same state, or you go to the first state or to the second state. Of course, what is the state means, it depends on the problem, as we will see. So we can model many problems to be Markovian chain as we saw it now. So this is and what is the probability that if you are in 0 state, what is the probability after 5 iterations to be in state 1? This could be usually measured as by, we say that you are start from 0, 1. What is the probability that after 5 iterations you become in state 1? So it becomes B01, and we put here 5. It doesn't mean that when you put 5 here that you take the order 5 of the probability. No, but it can be computed by taking the matrix. You take the 5th order of the matrix. So we have here, for example, we have here the probability matrix P equal to B00, B01, B02. Then we have B10, B11, B12, and here we have B20, B21, and B22. And then this is the transition matrix. If you take the 5th order of this transmission matrix, and then you look to B01 of the power 5, this one after taking the the order, then this will be the probability that you start from state 0 and you become in state 1 after 5 iterations of this process. Okay, it was explained here. Okay, so and also it was explained this when we take the 3 of this matrix, when we take 3 of this matrix, and we approve here that x00, it will be like 3 rotations of the state 0 and to become again in state 0. But again, as I'm always saying, that it is good, of course, to study the proofs, but it is not necessary in the course. The important thing is how to use it. Okay. Here also we have some like analysis, which I can skip now. It is not necessary in this course. Okay. And what I want to see here, and I will end after this example. We take this example that let us begin with the straightforward example demonstrating how to model specific scenario using Markov chain. Consider an orange is like bag containing 2 poles. So there's 2 poles in the bag, which can be either white or red. So the poles can be both white, it can be both red, it can be one white and one red. We don't know yet. We don't know how is the what contains inside the bag. Each draw involves selecting one pole. So you select one pole randomly, okay? And if it is red, if you find the pole red, it gets replaced with a white pole with a probability of 0.7. So now you have the bag. The bag contains 2 poles. We don't know anything about the colors of poles. And then you take the pole from inside the bag. You look to the pole. If you find it red, so you have to replace it with probability 0.7. You replace it with white ball, and you have 30% chance to rebut the same ball again. So it means that the ball, it can be replaced with the probability 0.7 with white ball, or it can be red again, of course, with the probability 0.3, because the total probability must be 1. And if it is white, if the draw ball was white, it gets replaced with a red ball with a probability 0.5. So if you find the ball white, then you can keep it with a probability 0.5, or you can replace it with red ball with a probability 0.5, 50-50. Okay, so now we want to formulate or model this uncertainty problem. So we have uncertainty here, and we want to formulate this problem. Okay, so now how to formulate the problem? They say here that determine the probability of having 2 red balls in the urn after 4 iterations. So after you repeating this process 4 times, what is the probability that inside the ball, or sorry, inside the urn or inside the bag, we will have 2 red balls? Okay, now assuming the initial state was x0 equal to 1. So we start with initial state equal to 1. It means that the initial state that we have only one red ball. Okay, what are the states that we have? We have this bag. We have 2 balls. Each ball can be red, or it can be white, or it can be red, or it can be white. Okay, it doesn't matter. So we have this bag, and we don't know what is inside the bag. So what are the states? The states that you have 0 red ball. It means that 0 red ball. What is the meaning of 0 red ball? 0 red ball means that both balls are white. Or you have the state 1 white and 1 ball, 1 white and 1 red, and you have the state that 2 balls are red. So those are the states that we have: 0, 1, 2. Okay, now we come to the initial problem, and we try to define what are the transition matrices that, or the transition probabilities that we have. They said that if you have what is the probability? You have 0 here. What is the 0? 0 means that both balls are white. Okay, so what is, if you draw one ball, of course this ball will be white because both of them, they are white. So the probability that you like keep the white is 0.3. So from 0 to 0 is 0.3. But the probability that you replace that white ball with a red ball, it is 0.7. So it means that you move from state 0 to state 1, because in state 1, now we have one red ball and we have one white ball. Okay. Okay, now we have one white and we have one red. So now you draw one ball from this orange now, or from this bag. Okay, now if it is white, then again, you will replace it with red with probability 0.3. If it is red, then you replace it with white with probability 0.7, as it was given. So now you can start to have the transition matrix calculations according to that, to the given numbers, until you reach to the 2. Of course, now if you have white, because both balls now, they are white. So the probability that if you get white, to replace it with white is 0.5, and the probability that you replace it with red, it will be 0.5. So there is a chance that you go from 2 up to 1 again, because you replace it already with a red ball. Now, when you read the text, you will find the details of how to calculate all these numbers, but you can see that all the details are given. All the details are given of all these numbers. But finally, I come up with this matrix. So this is the matrix of, it is called the transition matrix of this problem. And if you take the 4 iteration, it means that you repeat this process 4 times. You will get this matrix now. What that mean? Here, it means that if you start with no red ball in the urn, what is the probability that you will be again in non-red ball in the urn? So it will be 0.18. This is the probability. Okay. Okay. If you start with both white, what is the probability after 4 times to get one of them red? It will be 0.49, as you can see it here. So this information is given by taking the order, or the power of this transition matrix. Actually, this makes the analysis very easy. I mean, just imagine that if you have this problem and I asked you that find the probability that you will have 2 white after 20 times of making this operation, or this process. It can be very complicated without this Markovian process. In the Markovian process, first we define the problem. Okay, we define the probabilities. It was given in the text. After that, we build the matrix. Then we take the matrix of the power 20. That's it. We solve the problem. Okay. So the Markovian process, of course, there are some conditions in order to get this result, but I will not go through the deep details of this Markovian process right now. But just taking the order, then you can find the transition probability. Assume that this status is your wireless channel. So if you have wireless channel can be maybe defined as let me take some place. So maybe we can define that wireless channel, that very good channel, excellent channel. We have fair channel. We have bad channel. We have very bad channel, for example. Very bad channel means that it is faded. We have deep fading, and we are in outage in the channel. Okay, and then according to our transition, the transition matrix here, it means that you're transmitting symbols. So when you transmit symbol, what is the channel that it was observed by that symbol? It can be excellent channel, and from excellent channel, that the next symbol will be also excellent. So this is the problem of writing this, but yes. So now we have channels. Assume that we have channels like this, 4 channels, and this is excellent channel. Excellent channel means that you can use very high modulation level, so you can send very high data rate. So it is the excellent channel, maybe it is excellent channel, and then we have a good channel, we have a bad channel, and we have very bad channel. Very bad channel, it means that in outage. Bad channel, it means that you will send packets but at very low rate, and good channel you send at fair bit rate. So now we can study this as Markovian, because if you are in excellent channel, there is a chance, there is a probability that you stay in the excellent channel. There is a probability that next packet will go to good channel. There's a probability that from excellent channel we go to the bad channel. There's also probability that we go from excellent channel to very bad channel. So sometimes you are in excellent situation, but suddenly you go through deep fading. And now if you are in deep fading, you can stay for some time in deep fading, or from deep fading you can go to the bad channel, and you can go to the good channel, and you can go to the excellent channel. Also the same for the good channel, you can go to the excellent, you can go to the bad, you can stay in the bad in the good channel. From bad channel you can go to the very bad channel, you can stay in bad channel, and you can go to the good channel, and or you can go also to the excellent channel. So now for every probability we can put here the probabilities that B00, for example, B04, and so on. Okay, from where that we got these probabilities, we can receive these probabilities by measurement. So if we have measurement, for example, if you have transmitter and receiver, we have transmitter and receiver, okay, and we come to certain area, for example, and then we start to measure we divide, for example, if the signal to noise ratio that greater than 20 dB, then we have excellent channel. If signal to noise ratio is less than 20 dB, but less than greater than let's say 10 dB, we call it good channel. And so you define what is the signal to noise ratio for each situation, and then you start to look to the how was during the testing of the channel, how was the channel moving. For example, you have SNR. This is the SNR. It was in dB. It was 25 dB, then becomes 20 dB, then it becomes like minus 5 dB, very bad, then 10 dB, and so on. So when I look to this data, that if you bring me the data from, for example, from Al-Madar base station in El Guarcha, for example, and if you bring me all this data, let's say taken for one day, maybe you have hundreds of thousands of data, maybe 1 kilobyte of data. Then based on this data, I convert this data into states. For example, 25 dB, it is a state 1. 20 dB is still state 1. Minus 5 dB is state 4. And then based on that, I can calculate the probabilities. For example, I count how many transition from 25 dB to minus 5 dB, for example. How many transmission from state 1 to state 4. Then I count how many transition. The number of transition was 100 transition. 100 transition from how much data, from like how much data that I was in excellent state. In excellent state, I have 1,000 data. 100 of them was moving from the excellent transition or from excellent state to the very bad state. In this case, I know that probability from 1 up to 4 is equal to 100 divided by 1,000. Then this equal to 0.1. Okay, I can build all probabilities of this channel state transition, and once I find all, I found all probabilities, I can build my probability matrix. Now, my probability matrix will be 4 by 4 because here I assume that I have 4 states of the channel. Based on this probability matrix, I can compute the performance of my communication system. For example, the average data rate that I can transmit, and also I can optimize my radio scheduling in this channel according to this P. So actually, Markovian process is very important in wireless communication, as far as in many other applications, like also in machine learning application. We have what is known as hidden Markov model, but I will not cover it in this course, where the states are hidden, but I have observation. I have observation, but this observation can come from state 1, or it can come from state 2, it can come from any state. And from each state, it has another probability. So it is called hidden Markov models, but it is not covered in this course. So we stop here. Sorry that I take a lot of time from you today, but at least that now we have the Markovian process covered. There's another example here, so please study this example as well. I add also full code, octave code, in order to emulate this example. After that, we have the Brownian motion. Actually, Brownian motion, I am not going to give it in this course. Okay. The reason that I will skip this section, because this section is very important when we deal with like a stochastic differential equation. If you have also in estimation theory, when we talk about Kalman filters, continuous Kalman filter, for example, and in estimation theory in stochastic differential equation, it is crucial to know what is Markovian motion, Brownian motion, and how we can model the white noise. This is the way that to model the white noise. But since this part will not be covered in this course, so this course is not included. Sorry, this section is not included. So Brownian motion, the section 2.10.2 is not, all this is not included in this course. So you don't need to take care about all this part. Okay. Even it is interesting and it is important, but we cannot cover everything in this introductory course. And next week, inshallah, we will go through the modeling of dynamic system, and we will talk a little bit about what if you apply a random process x of t to linear system, which has impulse response h of t, what will be the characteristics of the result. So this will come by this one. We complete the material for this course. It is about, I can say that it is about 70% of what I had in my mind before I start the course, because this part will be important. So it might be completed in one lecture or 2 lectures. Okay. And actually, in my previous intention, I had the intention also to cover a little bit about the estimation theory. But I think we will not have time to cover the estimation theory. So this could be given in the future in other different courses. But let us stop in this dynamic modeling. So actually, this is what I wanted also to give from my book, is the estimation theory, chapter 4. But where we have Kalman filters, and they are very important in communication, but and also in generally in electrical engineering, control or power systems or telecommunication. But nobody knows. Maybe this could be given in different courses in the future, inshallah. Okay, thank you very much. And sorry again that I crossed the time. And I open now the time for questions. If you have any questions, I will just stop recording now. And yes.